So this course is going to be about review of classical physics, and I have basically two goals. One of them is to review theoretical mechanics, and so I will first basically review whatever you should know already from your undergraduate studies, and then I will also touch on some advanced topics. And so these advanced topics will be Hamilton-Jacobi theory. If you had very good course on theoretical mechanics, you already know what it is. But also, I would like to discuss constraints, and I would like to discuss integrability. So what does it mean that the system is actually integrable? And very intuitively, it means that you can actually integrate the equations of motion. So I will give you precise conditions under which actually you can do this. Okay, so that's the aim here. And then the second goal will be to review classical field theory. So classical field theory, and I will mainly concentrate on Maxwell's theory, which is really the cornerstone of modern physics. And so we shall see that basically from Maxwell's theory, you can immediately arrive at special relativity, but it's also a very good prototype for general relativity and so on. And so when we will be actually discussing general relativity, I will always compare with Maxwell's theory, and you will see that it's very, very similar. So everything actually, you can map one thing to another, and it's really beautiful. So Maxwell's theory is really, really nice, but of course it's also a gauge theory, which is like really all modern theories are gauge theories. It has the conformal symmetry, and so you have ADS-CFT and so on. So really Maxwell's theory is the cornerstone. Maxwell's theory. I will also briefly discuss the scalar field theory, which is not that interesting, but you will start from it when you discuss your QFT course. So, okay. So then I give you the syllabus or rough plan of what I'm going to discuss. And I'm going to start with Lagrangian mechanics and then Hamiltonian mechanics. And this should probably take this week. So 4 lectures. And then next week will be this classical field theory. So some of you I've noticed that you already printed out the study text for this. So it has only the first part at this point because the second part is not written yet, but I'm hoping to update it. And so what you have at this point is just about the first week, so about the theoretical mechanics, and then hopefully by next week I will have the second part. So now, of course, there will be lots of typos and lots of mistakes and lots of other things. So I welcome, I encourage you to find these mistakes and find these typos and tell me. And so that in the end we have a nice study text. I also encourage you to make your own notes because there is nothing better than your own notes. So now there's also classic books which I used at one point or another. So let me just mention Landau and Lifshitz Mechanics, which is a beautiful book, 100 pages long, but it has everything in it, and it's like beautifully written. Not all the arguments are actually correct, but the physics intuition is very good. And so I will actually follow this strategy. So I will not always present 100% correct proof, but it has the physical intuition. I'll try to be as physical as I can. Then there is complete counterexample to this is the Arnold's book, which is very mathematically precise, and it's like really advanced classical mechanics. Goldstein is the classical text. You probably used it in the past. So now regarding the classical field theory, I think Landau and Lifshitz, again, volume 2 is a very, very nice book. And it has everything. It has Maxwell's theory, it has gravitation, it has everything. So really, again, very, very nice book. So now, Carol will be mainly source for the relativity course, but maybe I will already use some of the things from there. Zwiebach is the introduction to string theory. We don't really discuss here the string theory, but we will discuss vibrations of string. And so I'll basically take that from that book. And finally, Dirac's book on lectures on quantum mechanics. It's a beautiful book on constraints, where basically Dirac builds the theory of constraints and how to deal with constraints when they arise. And so we will only use a little bit of that, like really the introductory part. But if you want to learn about constraints, Dirac's book is really, and it's really, really tiny book. It's, again, I don't know, less than 100 pages, and it has everything. So now I encourage you to have questions. So anytime I say something wrong or something is not clear, please ask me questions. Questions? All right. So let me start with Lagrangian mechanics. So part 1 will be Lagrangian mechanics. And part A is the Hamilton's principle of least action. Okay, and so I'm hoping that this is just a repetition for everybody. So I'll be going quite fast. So we want to describe the motion. And to describe the motion, we just choose some coordinates, qi. And we are interested in how these coordinates evolve in time. So this is how you describe your motion. So now these qi are so-called generalized coordinates. And so they don't need to be the Cartesian coordinates as you know them, but they can be whatever is convenient to describe your motion. So for example, if you want to describe the pendulum, it's really stupid to choose x and y or whatever this and that coordinate, because you would pretend that the system actually has 2 degrees of freedom, whereas it has only 1. It's the angle is the convenient coordinate which parameterizes your pendulum. So this can be any coordinates which are convenient, and you are choosing as many as the number of degrees of freedom. And if you choose more, you just complicate things. And in the end, you will have constraints. So for example, if I use x and y here, I am always constrained that x squared plus y squared equals to the length of the pendulum L squared. Okay, so then I have a constraint, and then I have to deal with this constraint. Okay, so that's how we describe the motion. So now when you discuss the Newtonian mechanics, typically you consider the initial value problem. So you specify, so at some time t1, you specify what your q at t1 is and what your derivative at t1 is. t1. And then you solve the equations of motion and you find how q looks at some later time t. Okay, so I specify 2 initial data, q and q dot. So now this is of course perfectly correct, but there is an equivalent formulation, which is the, if you want, boundary value problem. And so in this case, instead of specifying q and q dot at t1, you only specify q. And the same you specify for some later time, t2. So I fix my q here, and then I fix my q there. And so again, I'm providing 2 data, and so this should be enough to solve for how the q looks in between these 2. And so these are sort of equivalent formulations of your problem. So now we'll be using this one here, and it's actually the right thing to do if you. So for classical physics, it doesn't really matter, but it's very difficult to formulate quantum physics in the initial value formulation. So So the standard quantum mechanics typically uses this boundary value problem. This is in the heart of quantum gravity, described by loop quantum gravity, and so on. So this is typically the thing which is easier at the quantum level. Okay, questions? All right, so this is just the introduction. So now, of course, the central theorem is really, really slow. So now we have the principle of least action. And this is by Hamilton. And so when he formulated these things, he was less than 30 years old. So it's actually, he made this breakthrough, I think, at the age of 29. So, and it says, motion of the mechanical system in time interval t1 to t2. So I'm interested in how Q looks in between this t1 and t2. Coincides, or is given, coincides with the extremals of the action functional and so what is action functional? So, well, it is S, and it's a functional, so it's a function of a function, right? So function, and then function is my trajectory Q of t. So function of a function, and it's given by the integral from t1 to t2 of the Lagrangian, which depends on q dot and t in principle, although in many cases t is not explicit. So the dependence of L is typically on t is typically only through q and q dot. Okay, and so this is called the Lagrangian. And then this Lagrangian is, you know, some specific function of this q dot and t, which characterizes your motion, which characterizes your system. So specifying L, I specify the system, and then I can solve how the system actually behaves. Okay, so that's the beautiful result of Hamilton, and that's how you find the motion here. So now, this is all very nice, but how do we get the equations of motion? So really, I have to extremize. I have to find when I have to vary this delta S with respect to the trajectory Q, and then I have to set this equal to 0. That corresponds to the extremum, and that hopefully gives me the equations of motion for this. So as the standard picture you are all familiar with, so you have Q and T, and as I said, I fix at T1, I fix my Q, and then at T2, you fix your Q. So this is 1, and this is 2. And now, in principle, you consider all the trajectories which go from 1 to 2, but with these fixed endpoints. So this is fixed endpoints. Okay, so now I have one trajectory here at a given time. So this will be my trajectory Q of t. And then this trajectory will be Q of t plus delta Q of t. So this will be delta Q of t. And this is Q plus delta Q trajectory. And so this variation very, very important that when you vary and when you derive the equations of motion from here, the variation is such that you fix time, and at that given time, you just consider a different trajectory, right? So when you consider delta Q of t, time is fixed. So why I'm stressing this is that when you are deriving concept quantities using the Noether's theorem, which we will discuss in a minute, this is no longer true. You don't fix time there. So only when you derive the equations of motion and then you consider this variation delta. So to distinguish the two deltas which you do, the one for equations of motion, I just write delta, and for the concept quantities, I'll write delta tilde, and they are different variations. All right, so now what we want is that delta S, which is, if you want, SQ plus delta Q minus S of Q is equal to 0. So this is what you want to find, and that gives you the equations of motion. And since the time is fixed in this variation, you can sort of commute the time through the delta thing. I forgot that. So this is how your variation behaves. So you can commute the time derivative with delta variation. Trivial for everybody. Everybody's sleeping. It's great.
Question.
Yes.
It's not so trivial for me. Would you mind explaining why would that be the case?
Oh, it's just how you do the variation is that you fix the time, and then you consider one trajectory and then the other trajectory, right? So when I vary things, I don't do anything this time. And so that's why I actually commute this time, right? So if you want, time derivative motion is this one here. So this is how dt would behave. And the variation is this direction here, and they are perpendicular. And so there is nothing like I would be changing. Of course, you can define this mathematically, and then you can define the precise variation in the functional sense, and Dan will do that in his course. So then you can see how mathematically this is defined. But physically, it's like I am not doing anything this time, just fixing time and consider a different trajectory there. All right, so now you see that to do it physically, it's very, very simple. So I have to vary this delta S. And so I don't do anything this time. T1, T2. So the only thing which can vary is the Lagrangian inside. Okay, dt is not varied here because time is fixed. Okay, and so you can calculate that simply by calculating the partial derivatives. So L depends on Q, and then I have delta Q. L depends on Q dot, and then you have delta Q dot. And I'm not doing anything this time, so that's it. So this is how I vary the action here. So now, what is this thing here? It's delta d over dt of Q, right? So it's Q dot, so it's dQ over dt. And I can swap the two. So I can write this as d over dt of delta Q, because using that property there. And then I want to integrate by parts. So now I have the derivative here, and I want to shift this time derivative from this term to that term. And of course, I'm picking up the minus sign and the boundary term. And so this will be an integral from t1 to t2. And then I have dl over dq from the first term, and then minus d over dt, the second term, dl over dq dot, and then delta q and dt. So this is when I integrate it by parts, but I also pick up the boundary term plus dl dq dot delta q from t1 to T2. Okay. So this is just an integration by parts. Right? So now, however, the boundary term is 0. And it's 0 because I impose the fixed endpoint. So I know that delta Q at T1 is 0 because I'm fixing this point here. I don't allow any variations here. And similarly for time T2. So this thing is 0 because delta Q1 is 0 and delta Q2 is 0 by fixed endpoints. And so you can claim the victory in order this to be 0. So you require that this delta S is equal to 0. And that gives you the true motion. It fixes the trajectory. And so you find that the equations of motion, of course, the only possibility is that whatever you integrate here is 0. And so the equations of motion, which are called Euler-Lagrange equations, Euler-Lagrange is nothing else than dl over dq. If you have more of these, you can put this index I, and you get, let's say I have n generalized coordinates, so I have n equations of motion, and d over dt, dl dq dot I equals to 0. And that's your Euler-Lagrange equations, which tell you how the motion really looks like. Questions, comments? Everything is trivial. So just a few remarks. So just to wake you up, the first question is, what is the order of this equation? Is it fifth order equation? Or so tell me. Second order. Why is it second order?
Because we started from a Lagrangian that depends on Q and Q dot.
So that's already first order. And now I differentiate once more. So these are second order equations. So now how many initial data or boundary data I provided? 2, because I fix Q at T1 and T2. Can I solve this? Yes. So you have two conditions for second order equations, and that's fine. So now you will deal in your tutorial today with higher order equations of motion. They are typically bad, simply because they are bad. They have too many solutions, and some of these solutions actually behave unphysically. So that's why people don't want more than second order equations of motion. So for example, typical thing at the classical level which happens is that you have runaway solutions. That means that, for example, if you consider, I think, third order equation instead of second one, then you would have a solution where you start with a particle at rest, and suddenly, without any force, this particle starts accelerating and it moves to the infinity at the speed of light or whatever. So you have such solutions, which of course are unphysical, and so that's why you better describe your physics by second order equations of motion. At the quantum level, you have ghosts and stuff like that. So that's first remark. Second remark, I didn't tell you what L is, but typically for mechanical systems, it's just kinetic energy minus the potential energy. So I haven't derived this. I'm just saying, well, the way I treated it is whatever L is, this is my equation of motion, and L specifies my system, and this is how the system behaves. But you can show that it's actually connected to the energies of the system under some conditions as kinetic minus potential energy. If you're interested in the derivation of this, look at Landau and Lifshitz. So they have the derivation. They start from a free particle, and they show that in that case, you have to have 1/2 mv squared, and then they proceed to potential, and so on. Yes?
Can we always construct a Lagrangian?
If you have dissipation, no. Yeah, so it's typically this thing is working well for conservative systems where the energy is conserved.
So the principle of less action is just for
for certain class of systems, yes. you cannot always, yeah. But you know, in the field theory, if you cannot write down the Lagrangian, you typically consider the field theory to be bad. But there are such field theories where you cannot write down the Lagrangian. And if you talk to Davide Gaiotto, who is a faculty here, he's actually invented infinite number of theories which actually don't have Lagrangian description, but are nevertheless interesting and well behaved. Yes?
Like, if we have dissipation, can we just add I think they're called generalized forces or something?
Yeah, you can add generalized forces. Yeah. But
in that case,
typically, you know, nice systems have, you know, this description. Yeah.
So in those cases, the Lagrangian isn't exactly correct, but if we add the generalized forces to the right-hand side of this equation, we're going to get a good equation, right? So,
okay, very good that you said that. So for most of the physicists, Lagrangian is just a tool how to derive the equations of motion, and what is really important is the equation of motion. So some physicists consider Lagrangian something really, very important. Of course, the action enters the quantum description, right? So at the quantum level, the value of the action is important, and so on. So for that, it's actually important to write down the action principle. And if you cannot do that, you typically don't know how to deal with it. Yeah. All right. So the third remark is very, very simple. Is that there is a huge freedom in the description here, and so there's a freedom in the Lagrangian description, and that is if I find a new Lagrangian, which is function of q dot and t, which is the old one, q dot and t, plus a total derivative of a function which depends only on q and t. So this q dot is missing here. So if you write down a Lagrangian like this, so again, it's the old one plus a total derivative of an arbitrary function, which, however, depends only on q and t. It cannot depend on q dot. So then the statement is you get the same equations. Euler-Lagrange equations do not change. And so you may be inclined to say that this Lagrangian actually describes the same physics. Okay, so now, of course, you can show this very easily. One way is to take this Lagrangian here, plug it into the Euler-Lagrange equations, and do the painful differentiation, and find out that lambda really doesn't enter the description, and you end up with the same equations of motion as you started with. The other one is actually quite neat, so let me do it, and it's also simple, so why not to do it? So your new action is just given by L prime dt, which is the old action plus integral d lambda dt. But of course, I can integrate the total derivative. It's just lambda. It gives you just the boundary term. So this is s plus lambda t2 t1. So this is your new action. So now when you vary this new action, delta s prime, of course you get the variation of the old action, plus now this may look fishy, but it's okay. So you have delta q t2 t1. So this is how you vary your boundary term. Well, okay, if you do it properly, you'll find that this is correct. So now, but you still have fixed endpoints. So again, delta q t1 is 0 and delta q t2 is 0. So this term is 0, and you see that the variation of s prime is the same as the variation of s. Okay, so that's the sneaky way how to calculate this, and it's because of the fixed endpoints. So that is this freedom in the Lagrangian description, and such, so related Lagrangians describe the same system. Questions, comments? All right. So now part B will be integrals of motion. So now you derived your equations of motion. You know that they should have solutions because you have enough conditions. to solve them. But actually, in most of the cases, you cannot really solve them. And there are only, so of course, in your undergraduate physics, you only encounter the examples where you can solve them. And that only happens for integrable systems, for very, very special class of systems. So typically, so solving equations of motion, meaning Euler-Lagrange equations, you can do it analytically or almost analytically, provided you have integrable system. And integrable systems, of course, form measure zero subset of all the systems. So these are very rare. But fortunately for us, they are also interesting. So for example, the Kepler problem is an integrable problem, and you can actually solve it. Very rare, but I would say maybe quite important. So for the Kepler problem, you have the force which goes like 1 over r squared. So now, if you, for example, consider some influence of other planets or whatever, this force changes, and you add some corrections to this, and immediately that will not be integrable, and so you are screwed. But what you can still do is that if this correction is small, you can do perturbations around your analytic solution. So you can do perturbations. And so, because you can do this perturbation theory around something which you know, that's why the integrable systems are so interesting, because they are typically really, really interesting, but you can still go around, and if you perturb them a little bit, you lose the integrability, but you can still actually predict something. So perturbations. And finally, you can do numerics, and I can't do that, but some people can. Okay, so that's numerics. So what I will concentrate on in this course is just the first thing on the integrable systems, and how to actually, when you can solve these things analytically. I will not discuss perturbations, although they are very interesting, and I have no idea how to do numerics. All right, so to study the integrable systems, the key concept is these integrals of motion. So definition, an integral or constant of motion or conserved quantity of motion. I'll give you a very vague definition, but is a function and so it's a function I, which is a function of q dot, and t, such that di over dt equals to 0 along the trajectory for q of t, solving equations of motion. So basically, you can imagine that it's really something which is propagated along your trajectory. It doesn't change the value. So if I start this, I have my particle moving in my solar system. And so if I consider its energy here, as I move along the trajectory, the energy does not change. It just remains constant. So that's an example of an integral of motion. Okay. So that's the definition of what I mean by integrals of motion. You will see examples very soon. But what is really beautiful is that these integrals of motion are connected to the geometry of the problem. And you've probably heard about the most famous theorem as the Noether's theorem. So Noether. And so let me just formulate one version. So version 1, which is the most general one. It doesn't say anything, but that's why it's most general. So for every for every global continuous symmetry of the system, symmetry of the system there is a corresponding integral of motion. Okay, so that's version 1 of the Noether's theorem, the most general one. So it says like whenever I can find a symmetry, meaning, for example, the Lagrangian doesn't change in time. So as I evolve in time, the Lagrangian stays the same. Then there is a corresponding concept quantity, and meaning there is a corresponding constant of motion. And in this case, it would be like a generalized energy. Okay. So what is really beautiful about this is that it sort of geometrizes physics. There is a one-to-one correspondence between the symmetries of the configuration and phase space, and it gives you the corresponding concept quantity. Okay. So now I haven't explained what global continuous symmetry is. It's a symmetry. So I will consider a very special class of these symmetries, which I'll write in a very confusing way. Okay. So whatever. So now, in order to understand this, so what type of symmetries or types of symmetries we have? And as I said, I will just use very, very special form of things. So we can actually change the coordinates, we can change time in the Lagrangian, and then under the change of these coordinates and under the change of time, we are just looking at whether the Lagrangian or the action actually changed. If they didn't, we have a symmetry. Okay, so we can consider transformations like going from time to t prime, which is t plus delta t. I can change time to t prime, and in the same way I can change my generalized coordinates to generalized coordinates which are now functions of this new time t prime, which will be my original one plus delta q. Okay, so notice here that I introduced this delta tilde. It's a different variation than this variation here. So this variation here kept the time fixed. This variation here, if you look at here, I am considering q prime at t prime minus q at t. And that's given by this delta tilde. So this actually changes time. And so it's a different type of variation. So in other words, here we have this picture here. So in the equations of motion, you consider the delta, which is just you fix time. This is my t, and this is my delta q. And so you really fix time and consider the variations here. In the Noether theorem, you consider delta tilde. So this is your q, this is your t. So now you can change both t and q. So you start with t, but then you go t plus delta t, delta tilde t. And so I can change q from here to q from there. So this is q plus delta q, and this is my q. So now you are changing both. You are changing. You are moving in this direction, but you are moving also in that direction. Another difference is that when you consider the equations of motion, you fix your endpoints. right? So that's how we formulated the thing. We have this thing here, which is fixed, 1 and 2. And so here, you have, when you are deriving this, you have fixed endpoints. However, when you consider the Noether symmetries, you are interested in transformations which need not respect these fixed endpoints, right? So for example, I'm interested, what happens when I move the system from here to here? Is the Lagrangian invariant by that? But if I move the system from here to here, I certainly do not necessarily preserve the fixed endpoints because I'm shifting everything by some distance. So there are no fixed endpoints, and so in principle, your variation here looks like this. So I don't have to have fixed endpoints. You can just shift something which from here to there, and that's the type of variation you consider in these cases. Are there any questions to this? So different type of variation. And of course, if I fix the endpoints, I can integrate by parts, because I am guaranteed that the boundary terms which I integrate by parts actually vanish because of the fixed endpoint condition. If I have this type of variation, I don't have fixed endpoints, and I cannot integrate by parts. Well, I can, but I cannot throw away the boundary terms. And it's precisely the boundary terms which give you the concept quantities. Okay, so as we shall see in a minute. All right, so that's which type of transformations we consider. So now I'll write them in very confusing way. So we have this type of transformation. And then I'll write this delta tilde t. And this is really stupid notation. I apologize for that. But I'll just explain what I mean by that. And delta tilde q is delta is epsilon times delta q. So what I mean by this notation is that epsilon is the parameter how much of the transformation I do. So parameter which tells you how big the transformation is. So for example, I rotate in this direction, and epsilon tells me rotate by 1 degree or rotate by 90 degrees or whatever. It tells you how big the transformation is. And this thing tells you it's the generator of the transformation, which tells me what type of transformation I'm considering. Am I rotating this direction? Am I rotating that direction? Am I moving from here to there? It's like a generator of the transformation. It tells you what type of transformation I'm doing. What type of transformation you consider. So a few examples. So now we discuss what type of symmetry. So we consider these transformations and we write them in this stupid way. And then we can divide the symmetries based on what these things are. Symmetries. So first, you can have discrete, or you can have continuous. So the one which enters the Noether's theorem is the continuous symmetries. And of course, by discrete, I mean I have, let's say, a square. And to get a symmetry, I have to rotate that square by 90 degrees. And if I rotate by anything else, if I rotate by 1 degree, I don't get the same thing, right? So this has a discrete symmetry. I have to rotate by a precise angle and its multiples. Okay, so that's a discrete symmetry. Similarly, if you have a lattice with distance a, if I want to move the lattice on itself, I have to move it by this distance a or its multiples. I cannot move it by an arbitrary small. So continuous means, so discrete is that this epsilon is finite number and it's given, finite given number in order to get the symmetry. of course, the continuous symmetry is such that epsilon can be infinitesimal, can be arbitrarily small. So epsilon is arbitrarily small. And so an example is I go is a circle, and no matter how small rotation I perform or whatever the rotation I perform, it will rotate into itself. And so that's an example of continuous symmetry. Okay, so now we know what continuous symmetries are. So now you have also another thing, which is either you have global symmetries or you have local ones. So you're probably more familiar with these things from field theory, but the global ones have epsilon equals to constant. So and the local one have epsilon as a function of time. So at this given time, I do the rotation like that. At later time, I do a different rotation or whatever. So that would be so if you can find a symmetry of the Lagrangian which depends on epsilon as a function of t, you would say that Lagrangian actually has gauge symmetry. If it's under epsilon equal to constant, you will have global symmetry. So now these global symmetries, they give precisely Noether's theorem, as we discussed, and they give you the conserved charges. Sorry, there's no space here. Can you still see it? Conserved charges. If you have local symmetry, so you have gauge symmetry sometimes, it's called, then there is another Noether's theorem, which is not the one I stated here, and it doesn't give you the conserved charges, but it gives you the Bianchi identities. It gives you some restrictions on equations of motion. It gives you something which is valid irrespective of equations of motion. So Bianchi identities. And they were discussed in the same paper by Noether. So she has several Noether's theorems. Typically, people only interested in those discussing conserved quantities. That's the first Noether theorem. And it's about these global and continuous symmetries. And I will restrict in this course on these global symmetries. But if you have local ones, you have gauge symmetries, then you also get something interesting. And that's these Bianchi identities. All right. Questions? So now the Noether theorem, as we said, requires continuous and global symmetries. Yes?
Are there any Noether theorems for discrete symmetries?
No. As far as I know, no. So in the lattice, you don't have conserved quantities. Other questions? All right, so this is all theory. So let's now be very concrete. So we have this version 1 which just tells you if there is a symmetry which is continuous and global, then you get the conserved charge, but it doesn't tell you what this conserved charge is. And typically it's an art to find the conserved charge. There's no procedure which you would just follow, and it would give you the conserved charge. But I can give you an explicit version of this. So Noether theorem version 2, which would be the explicit one. And so this is let delta tilde be a global continuous symmetry. Very good. I still forgot to introduce one more time. I'll just tell him. Okay. That means that is off shell. We find delta tilde t and delta tilde q such that delta tilde s equals to 0. So you find such variations of your time and of your generalized coordinates, let's say of this form here, so that the Lagrangian, well, so that the action doesn't change. Then the explicit form of this integral of motion which exists is given by dl over dq dot delta tilde q, and then plus L minus q dot dl over q dot delta tilde q. Okay, so this is an explicit form of this integral of motion. So now I used, okay, very good. Let me finish it. And so this is an integral of motion, and this will be satisfied on shell. So now what I mean by this on shell and off shell, anybody knows?
That satisfies all of the equations.
Aha, exactly. So that's on shell? That's on shell. So very good. So on shell means equations of motion are required so if you say some statement is valid on shell, it means that that statement is only valid provided the equations of motion are satisfied, are required here. On the other hand, off shell means it's valid all the time, no matter whether the equations of motion are satisfied or not. Okay, so now look at the beauty of this thing here. So what I require is that if I can find such a transformation delta tilde of t and q such that delta s is 0 of shell, so means I cannot use equations of motion to prove that delta s is equal to 0, right? So I have to really obtain this equality no matter whether the equations of motion are satisfied or not. Then this is a prescription for my conserved charge. But the conserved charge will be only conserved on shell only when the equations of motion are satisfied. Of course, because integral of motion is valid only on shell, right? So this is sort of trivial, but really I want to emphasize that delta s equal to 0 has to be valid no matter of. So you cannot use the Euler-Lagrange equations to show this. So that's the subtlety of this Noether's theorem. Okay, so example. So let me consider time translation symmetry. Translation symmetry. So what I mean by that is that, for example, well, it's at the level of action, but in the simplest way, your Lagrangian does not depend on time explicitly. So you can still depend on time through q and q dot, but it's not an explicit function of time. So if that is true, then what is my delta tilde t and what is my delta tilde q? What do you think? So now you have to find a transformation which leaves your action invariant, right? So I have to vary the action with respect to these delta tildes, and then I have to use some delta tildes in that action so that the action doesn't change. So you can achieve that by simply shifting t by some parameter epsilon and not doing anything with q. So you can check that if you vary your action and you use these variations and L does not depend on time, you will do it in today's tutorial. So don't worry, you will not miss the calculation. Then if you do this transformation, then you find a symmetry. So if you do this, you find delta tilde s equals to 0. And then if you look at this general formula here, well, delta tilde, okay, big mistake, you should have told me. This is delta tilde t, sorry for that, big mistake. One of them has to be t and one of them has to be q, otherwise it's screwed up, right? So, okay, so we have these variations here. So now the conserved quantity I is just, so this guy is 0, and this is just epsilon. So epsilon doesn't matter. So I can have just this conserved quantity here. That's L minus Q dot dl over dq dot. And that's your conserved quantity here. And because you have time translation symmetry, you intuitively understand that if nothing depends on time, there should be conserved energy. So this is generalized energy. Or energy. So that's first example. Second example is even simpler. So before I go to the second example, let me just convince you. So the proof of this theorem is constructive, meaning you can actually really construct this I, and if I have time to prove this, probably not, then I'll show you how you construct this integral I. And you will do it in your tutorial, provided this thing here. So really there's a way, if you observe the symmetry, how to construct this I. The problem is to observe the symmetry, right? So sometimes the symmetry is not obvious at all. And so it's very, very difficult. It's an art finding symmetries of your systems. And if you can find one, typically you can integrate the system, and you are famous. You write a paper, and the system is named after you, right? So, okay. So it's difficult. But so once we have that integral of motion, it's typically very simple to check that this is really conserved. So let me do it. So prove it is conserved. And it's a one-line calculation, otherwise I wouldn't be doing it. So you want to calculate di over dt, and you want to show that this is equal to 0 on shell, provided the equations of motion are satisfied. So what we have to, so we just have to dot this thing here. So it's d over dt okay, of L, and then minus d over dt of q dot dl over dq dot. So now what is dl over dt? So L depends on q and q dot. So this is dl over dq q dot plus dl over dq dot q double dot. So that's dl over dt, and then minus. So now I have to use the Leibniz rule. I have product of two things, so it's minus q double dot dl over dq dot, and then the second term is minus q dot. Oh no. What is it I'm doing? dt, or maybe I don't need to write it explicitly. dt dl over dq dot. All right. So that's that. So now you see that this term precisely cancels that term. And then if you factor q dot, you just get the Euler-Lagrange equation. So this is 0 by the Euler-Lagrange equations on shell, provided the equation. So to check that this integral of motion is really that this quantity is really an integral of motion on shell is simple. To derive that this is a conserved quantity is more complicated. Okay, provided the given symmetry. Questions? Example 2, even simpler, is space translation symmetry. So now you say that you have space translation symmetry if L does not depend on some generalized coordinate Q. That special coordinate Q is called cyclic coordinate. Cyclic coordinate. So if this is true, then you can show that the transformation, which doesn't change time, this time, so delta t tilde is 0, but delta tilde q is epsilon. Okay, so then you can check that this leaves the action invariant, provided that L doesn't depend on this q. And so now if I use my general procedure here, so now delta tilde is 0, so dl over dq dot is conserved. So I dl over dq dot is conserved, and it's called generalized momentum. Okay, and so this is actually obvious from the Euler-Lagrange equations. So remember, the Euler-Lagrange equations are dl over dq minus d over dt dl over dq dot is equal to 0. So now I'm saying L doesn't depend on q, so this term is not there. And then you get d over dt of something is equal to 0, and that something has to be integral of motion. Right, it's precisely the generalized moment. So this is even simpler to prove than the first one. All right, questions?
I have a question.
Yes.
In classical mechanics, I'm saying not relativistic.
Yeah.
Does the Lagrangian has to be a scalar?
What else it would be like? You're interested if it can be a vector?
It could be a vector, yeah.
I have never seen that. And typically, what you are asking is an interesting question, which people try to rephrase in other formulations. So when we will discuss the Hamiltonian mechanics, the Hamiltonian is just a Legendre transformation of your Lagrangian, right? And so what we are basically saying is that, yeah, we can describe motion of any system by one Hamiltonian or by one Lagrangian, by a scalar quantity here. So now, this actually is not obvious at all that you can just describe everything by one function. And people actually looked at, and it was Nambu who looked at the case where he considered more than one Hamiltonian, more than one Lagrangian. And you can still formulate consistent mechanics with more than one function like that. And it has the same properties as the standard Hamiltonian mechanics, but it's just more complicated. The problem is that at this point, nobody found an interesting example which would actually, so that this is useful for anything. Well, it's useful for some things, but there is no system which you cannot describe by standard Hamiltonian mechanics, but can describe by this Nambu mechanics, by this generalization. At this point, there is no such examples. So everything as we know it can be described by just one quantity here. But there are such formulations, and I will show it to you if you are interested at the end. Of course. Other questions? So now, let me just show you how the proof goes of this theorem. So what I will be now doing is to prove this explicit version of the Noether's theorem, and really to show how the calculation goes. And just have in mind that that picture which I drew some minutes ago is that the variations now need not to have fixed endpoints, and they change both time and q. All right. So proof of theorem version 2. And so for this, what you really need to understand what these variations are. So let's call it relation relationship between the standard variation as you know it from equations of motion and delta tilde. Okay. So the way I define it here is so delta tilde on t is just the difference between the times. So I can certainly write delta tilde of dt. Well, what I mean by that is dt prime minus dt from that equation here. And you can write it as d of delta tilde t. And you can also write it in a complicated way just by dividing by dt and multiplying by dt. Okay? So when acting on time, this delta tilde behaves as you would expect. Okay, so this is very simple. However, when it acts on functions, and more, so I'll prove that for just function of just q, but it will be valid for any function of q and q dot actually. So anyway, so let's do it for q. So by definition, this delta tilde q of t is just q prime at t prime minus q at t. Okay, so this is q prime t prime minus q at t. So now what you want to do is that you want to compare the things at the same time, right? So I need to relate this t prime to my t, and I just do it by Taylor expansion. I just consider that t prime is basically t plus delta t, and do the Taylor expansion. So this is q prime at t plus delta tilde t dq prime at t dt plus higher order terms in the Taylor expansion, and then minus q of t, which I had before. Okay, so this is just Taylor expansion, just expanding t prime to evaluate in t. All right, but now if you look at this term here and that term, it's precisely what the normal variation delta means, right? So the normal variation delta is q prime at t minus q at t. So this is delta q at t, and then keeping just the first order term here, is this thing here. So it's plus delta tilde t dq prime at t dt. Okay, plus other terms, higher order terms, which I neglect. But I can also delete this prime here, because q is very close to q prime. So they are different by the order of epsilon, right? The difference is very, very small. But I already have all the epsilon here, delta tilde t. That's already of the order of epsilon. So this will be also true, plus higher order terms. Okay, so this is your result, because I'm throwing away higher order terms in epsilon. Okay, so now you can write it in a clever way, which will be valid. So this is for q, but you can do it for any function, and you are getting a relationship. The statement is you can do it yourself. So for any function, of q dot and t, we have the following identity: delta tilde is equal to delta plus delta tilde t d over dt of that function. That's an identity which will be valid for any function. If you look at here, I derived it for the function equal to q, right? So I have delta plus delta tilde t d over dt, and I'm just stripping off this result of this qt. So that's the relationship between delta tilde and delta and other things. Okay, so once we have that, the proof is simple. Are there any questions to this? So as I said, I showed it only for Q. If you want, use this result to show it for any function of Q and Q dot and T. All right. So now the actual proof. So we have, by assumption, delta tilde S equal to 0. As the assumption that we found such a transformation which off-shell leaves delta tilde S equal to 0. So that's the assumption. Okay. That's the assumption. So now what is this guy here? So now, similar to deriving the equations of motion, I want to apply this delta tilde on whatever is underneath the integral. So this is the integral. But now, so the integral of L dt, but now I can change the delta tilde, actually change both. It changes L, but it also changes T. So I will have two terms. So it's delta tilde of L dt plus L delta tilde of dt. Now the variation delta tilde acts on both. Right? So now I use my wonderful identity for L. So I can relate this delta tilde to delta plus whatever. So this is integral of delta L plus delta tilde T dl dt, and then plus whatever I had before, delta tilde dt. Okay, just using the identity over there. So now if you look at this thing here, it's just d over dt.
Should be a dt multiplier.
Yeah, should be.
Sorry? Say it again?
I mean, delta tilde L and you have a times dt.
dt here?
Yeah. And,
And the
First one as well.
and the first term.
And the first one as well, yes. Thank you. Interesting. So now the statement is, this can be written as d over dt of L delta tilde t. Hopefully that is correct. So delta tilde and d over dt, they commute for time only. So I can do it. I can swap these two here. And then this hopefully is right, dt. Okay. So we have that. So now, by the way, look at this, right? So what is this, by the way? So I have just the normal delta tilde L dt, which is what I called delta of S. Delta of S plus whatever I have here, which is the integral d over dt L delta tilde t dt. Okay. So this is what you have. So you see that the second term is just a boundary term. Okay. If you are on shell and you have to fix endpoints or whatever, then this thing actually doesn't matter. So this is just a transformation of Lagrangian by a total derivative, right? So this thing is the symmetry of the thing. So I can throw it away. It gives the same equations of motion. This is just a boundary. So whatever. I just notice that delta tilde of S and delta S on shell or whatever are the same. But I cannot throw this boundary term because I don't have fixed endpoints now. All right, so now let's write this delta L. So it's an integral. So what is delta L? So delta L is dl over dq delta q dot delta q plus dl dq dot delta q dot. The same thing as we were doing before. Now dt dt plus the other term plus d over dt L delta tilde t dt. Okay, so this is still, I'm just continuing this expansion here. This is what it is. Now you integrate by parts as you did for the equations of motion, shifting the derivative from here to this term, picking up the boundary term. So this is dl over dq minus d over dt dl over dq dot delta q dt as before. And then picking up the boundary terms, I have an integral d of dt L delta tilde t is this term. And then from integrating by parts, I have also the term minus d over dt dl dq dot delta q.
Plus.
Is it plus? dl over plus. And is it correct? dl dq dot like that. Maybe.
You're supposed to be taking, like, you're taking 2 time derivatives of that last term, right?
So just shift the first bracket to
Like this.
d by dt acts on
that-
both of those.
That works, yeah.
Okay, I'll write it like that, and I believe you. So it's delta q like that. Is it? No, like that.
Yeah.
Yeah, finally victory. All right. So this is what it is. And it just comes from integrating by parts, which I screwed up. But it's very, very simple. Okay. Very good. So now we are on shell. So on shell, these are the equations of motion. So this guy is 0. And this is 0. Which means that whatever stands here, let's call it I. If I evaluate it on the boundaries, I will have I evaluated at t2 minus I evaluated at t1 equals to 0. What you are getting is I at t2 equals to I at t1, right? Because the whole thing is 0, right? So which is conservation, right? So for any t1 and t2, this will be true because now t1 and t2, they don't play any interesting role because they don't have fixed endpoints, right? So on shell, this guy is 0. This is a total derivative, so it's I t2 minus I t1 equals to 0, so this must be true. So the statement is, whatever this I here is the conserved quantity, is the integral of motion. So I is the conserved quantity. Okay. And so what this conserved quantity is I is L delta tilde t plus dl over dq dot delta q. Well, it's almost what I have given here, except that this thing here is written in terms of delta tilde q and delta tilde t. That one is written in terms of delta tilde t is fine, but in terms of delta q. So the last thing you have to do is to write the delta q in terms of delta tilde q and delta tilde t, and you will see that you will find this. Okay, so this is the constructed proof how we actually find this integral of motion. But as I say, the explicit finding of these integrals of motion is very, very difficult because it's very, very difficult to find which transformations leave your Lagrangian or your action invariant. And that's very, very difficult. You don't know a priori there is such transformation, but if you can find it, you won the lottery, and you can actually integrate the thing. So let me stop here. So now in your tutorial today, so we saw 2 versions of this. So first version is very, very general. It tells you there is an integral, but it doesn't tell you how to find it. Here I'm giving you, if you find the transformation, this is the integral. It's an explicit version. It really gives you the integral, but it's quite ugly, right? So now there is version 3, which you will discuss in your tutorial. That's the sneaky version. That's the version that doesn't make any sense, but it's actually very powerful in finding the integrals of motion. So what you will do in the sneaking version is that you will consider the global continuous transformations, but suddenly you will promote these global continuous transformations to the local ones. So suddenly your epsilon will depend on time. And then this trick actually allows you to extract the integral of motion explicitly for for things, but it doesn't make any sense in some sense. But you will see it's very, very powerful, and string theorists really like this version. So you will study it in your tutorial today. Questions, comments? Yeah.
I just got lost in the last part when you go from E, T, L, delta.
This one here?
Yeah. And
no. So all what I'm doing here is this should be just rewritten as is. But now what I'm doing is that I'm moving, as I did in the equations of motion, I'm moving this dot on this term.
Right.
So as you're deriving the equations of motion, but you are picking up the boundary term. And so the statement is that the boundary term is this one.
Oh, okay. That's
So I just screwed it up. Sorry for that. But it's just as whatever you are doing when you are deriving equations of motion, but now you don't throw away the boundary term because it's the boundary term which gives you the integral of motion. Other questions?
So that very last term on the bottom line, it doesn't have any delta tildes, right? So it seemed like that should only represent like a variation like we did when we derived the equations of motion, in which case, for that, the boundary...
So, sorry, which one? This one?
Yeah, so sorry, the second part of that, at the very end of like the...
This one here.
Yeah.
Delta Q. Well, but I can relate delta to delta tilde through that thing. So that's the last step which I didn't do here. Yeah. So at this point, I write it as in terms of delta Q. But in order to actually have the nice integral of motion, you have to write it in terms of delta tilde Q. And so you should get that result there.
So even though we write it exactly the same as we did in the equations of motion case, it's now...
So basically, the only thing which is different, what you are adding, is this term here, which you didn't have previously, because delta t is 0 by definition, but delta tilde is not. Yeah. Otherwise, it's precisely what you are doing in equations of motion. You don't throw away the boundary terms.
But even though this term looks exactly the same, it no longer vanishes, this last term.
Yeah. Okay, so see you in the tutorial.